class? Okay, let's do this. All right, guys, welcome back. I hope you had a nice spring break. I didn't go anywhere, but I got a lot done around the house. So that was good. We are starting chapter 6. Guys, chapter 6 starts our trigonometry unit, and that's it. We are trig for the rest of the year. This is some of the most important stuff to prepare you for calculus. So I think some of it you've seen, some of it will be new. We're just going to go with it, all right? So we are here. It's, I think, chapter 6, 7, and maybe we can get to a little bit of 8. And that'll bring us to the end of the year, guys. All right, so here we go. Trigonometric functions. Trigonometric functions, also called circular functions, sine, cosine, tangent, are functions of an angle. So these are functions that are going to depend on an angle measurement. They are used to relate the angles of a triangle to the lengths of the sides of a triangle, right? SOHCAHTOA, sine, opposite over hypotenuse. The measure of that angle depends on the length of the sides. They are important in the modeling of periodic phenomenon, among many other applications. So anything that kind of repeats over and over and over again, we can use trig functions to model that because they are periodic, they are repetitive. All right, so just to make a note, it is quite common to use Greek letters to denote angles, just so we're all aware of what probably the most popular Greek letters that we use are. We got our favorite theta. We have alpha, which really looks more like that a little bit. It kind of gets lost in the computer symbol. Then you have beta. Then you have gamma, which kind of looks like a Y a little bit. And I'm going to add one more just so we're aware of it, because it does come up with, I think, the cylindrical that we do is omega, which kind of looks like a curvy W. Just so you're all aware of some popular symbols that you'll be seeing. Okay, so what's going to happen is, right now we have angles. We're going to try and take trigonometry and all of these angles to the coordinate plane. By taking it to the coordinate plane, there's literally going to be no angle that we can't create. We can create positive angles, small angles, big angles, negative angles. So we're going to take them into angles of rotation. And by doing that, right now, trigonometry, it's all based off of a right triangle. Well, all right triangles have a 90-degree angle and then 2 acute angles. So all the angles inside of a right triangle are less than 90 degrees. Well, by taking it to the coordinate plane, we're going to be able to fit any angle into a right triangle, technically, all right? So when you have angles of rotation, it's an angle, it'll be in standard starting position if the vertex of a ray is at the origin of a rectangular coordinate system and its initial side is on the positive x-axis. So guys, angles of rotation, they come in 2 forms, positive and negative. They start with a vertex at 0, 0, and then a ray that lies right on the positive x-axis. So basically, guys, right now, this ray is representing 0 degrees. You haven't rotated it at all. It's laying right on the positive x-axis. So when you rotate in a counterclockwise motion, that creates a positive angle. So right now, that'd be like 30 degrees. Right? A little bit more, maybe we're at 45 degrees. Now we've rotated to 90 degrees. Now we're at 100 degrees, and so on. Until wherever you stop, a second ray is formed, and that is where the angle ends its rotation. So we call this ray the initial side of your angle, the initial side or the initial ray, and the initial side always starts on the positive x-axis. And then wherever you end, we call this the terminal ray, or the terminal side of your angle. All right, and we'll just call this one roughly 100 degrees, just to give you a visual. So each quadrant, I should say this first, if you rotate all the way around, you've made one complete revolution, one complete circle, and how many degrees live inside of a circle? 360, which means each quadrant represents 90 degrees worth of space. So here's positive 90 degrees, here's positive 180 degrees, go another 90, here's positive 270 degrees, rotate all the way around, you land at 360 degrees. So notice, because you are in a circle, things are going to start to repeat. This is the periodic part. So 0 and 360 degrees land in the exact same spot. If I go again a little bit more, if I go all the way to there, then that's 360 plus 90, 450 degrees lands in the same spot as 90 degrees. So this is where the repetitiveness comes in. There's going to be a lot of angles that land in the exact same spot, but they're actually not the same measurement. We call that coterminal angles. They are different sizes, but they land in the same spot. All right, then you do the same thing for negative angles. You start with a ray on the positive x-axis, but now to create a negative angle, you go clockwise. So this would be negative 30 degrees. This would be negative 60 degrees. This is negative 90 degrees if you rotate all the way to there. If I go a little bit more, this is where negative 100 degrees would be when you rotate in that clockwise motion. So again, this is your initial and this is your terminal side. And each quadrant represents 90 degrees worth of space. So this is 0, negative 90, negative 180, negative 270, and then all the way around brings you to negative 360 degrees. So just the way you rotate depends on whether you're creating a positive or negative angle. And then just don't forget, we have quadrant 1, we have quadrant 2, quadrant 3, and we have quadrant 4. So if you've ever wondered, why the hell are the quadrants numbered like this, thinking that we read left to right, why couldn't it be like quadrant 1 is here on the left starting? They rotate this way. So an angle will literally start in quadrant 1, in quadrant 2, to quadrant 3, to quadrant 4. They rotate through the quadrants in order. All right? Now, angles are either going to land in a quadrant, like 0 to 90 is in quadrant 1. 90 to 180 is in quadrant 2, 180 to 270 is quadrant 3, and then 270 to 360 is quadrant 4, then they repeat. If you land right on an axis, then we don't call you in a quadrant, we call you a quadrantal angle. And you are either on the positive x-axis, the positive y-axis, the negative x-axis, or the negative y-axis. I have that somewhere, we'll fill it in. All right? So angles of rotation, oh, here it is, will either lie in one of the 4 quadrants, or they rely on the x or y axis, in which case we say it is a quadrantal angle. It's in between quadrants, it's not actually in a quadrant. Okay, so guys, one complete rotation or revolution around will equal a circle, and therefore one complete revolution is 360 degrees. So one lap around the quadrants and you've got 360 degrees. So that means 1 degree, guys, is 1 out of 360. It's 1/360th of a complete revolution. 90 degrees is 90 out of 360. That's 1/4 of a complete revolution. 60 degrees is 60 out of 360. That's 1/6 of a complete revolution. And then 180, a straight line all the way to here, you create a straight line, is 180 out of 360. That's half of a complete revolution. All right, let's draw some angles just to get the feel for it. All right, so guys, draw each angle in standard position. You're just going to do an estimate. So maybe yours will all look a little bit different. It's really just as long as you're in the right quadrant, you're going to be fine. So they want you to draw an angle that is 135 degrees. So give yourself a coordinate plane. Your angle always starts on the positive x-axis. If I want to create positive degrees, I go counter. So there's 90. If I go all the way to there, that's 180. So I've gone too far. So 135 is somewhere in between 90 and 180. So all you have to make sure is that your terminal ray lands somewhere in quadrant 2. As long as your angle lands in quadrant 2, you are correct. And that we could say is about 135 degrees. All right, where's negative 120? What quadrant is he going to land in? Well, if we want to go negative, we got to go clockwise. So we start at 0, I go to negative 90. If I go all the way to the next quadrant, I'm at negative 180. So I've gone too far. So negative 120 is going to land somewhere in quadrant 3. So as long as you stop your angle somewhere in quadrant 3, you're right. All right, 226 degrees. I want to go counterclockwise. I want to get positive. So I'm going to go 0 to 90. Then I want to go to 180. I got to keep going. If I go all the way to the next quadrant, I'll be at 270. So I don't want to go all that way. So 226 is going to land somewhere in quadrant 3. All right. Negative 90 degrees. I got to go negative, so I want to go clockwise. And I'm literally going to stop right at the negative y-axis. This is negative 90 degrees. That's not in a quadrant, it's a quadrangle. Sometimes they'll let you say it's quadrangle, and then sometimes they'll make you label it as the negative y-axis. They make you describe where it lands. It's on the negative y-axis. All right, and then last 405 degrees, guys, that's positive. So we want to go counterclockwise, and it's more than one rotation. We got to go all the way around to get to 360. But if I go to the next quadrant, I have 360 plus 90, that would be 450. So I don't want to go all the way through. I want to stop somewhere in quadrant 1 again. So 405 degrees. So guys, if you think about it, this is where the repetitiveness comes in. We went all the way around, we got to 360, right? Then we had to go 45 degrees more to get to 405. So technically, 45 degrees and 405 degrees, they land in the exact same spot. So all of their trigonometric values, their sines, their cosines, their tangents, they're all going to be equivalent, whether it's an angle that is 405 degrees or 45 degrees, because they land in the exact same spot. So some of you are like, well, how does trig apply? Well, guys, once we get our angle set, we're always going to be able to construct a right triangle that an angle will fit in inside one of these quadrants. So we're going to be drawing right triangles like crazy off of all of these angles, and that's how the trig is going to apply. We're going to draw our angle and then construct a right triangle. All right, perfect. So those are angles of rotation. Everybody okay? Thumbs up at home, nice and easy, hopefully. Okay, so now I need you guys to understand that in the world of math, when you're dealing with measuring angles, degrees, even though it's probably the most comfortable way for us to measure an angle, it's not the best way when we're doing a math problem. So it's not the only way to measure an angle. So different ways to measure an angle. Yes, we can measure an angle in degrees like we all love and know and are nice and warm and fuzzy and comfortable with. But another way to measure it is in degrees, minutes, and seconds. And then the third way, which is going to be our best friend, the way we're going to use for the rest of the year, is in radians. Usually you come to me already knowing about radians. You've seen them in science classes sometimes, even in Algebra 2. I don't know how far you guys got last year. Radians is by far the most important. And guys, it makes sense. If we were going to measure this classroom, I could measure it in feet. I could measure it in inches. I could measure it in meters. I could measure it in yards. It makes sense then, since we have all these different types of measurements, that we have more than one way to measure an angle as well, okay? All right, so you already know degrees. We saw angles of rotation. We're gonna do degrees, minutes, and seconds, and then I'm gonna stop. I'm gonna save radians because it's so important for tomorrow, and I'm gonna do the whole day on radians tomorrow because we are gonna be using it all the time. So let me show you degrees, minutes, and seconds. And this is something that your calculator can do. I'm going to show you how to do it on your own first, and then we're going to check our answers on the calculator.
So we need calculators for this?
Yeah, you need a graphing calculator. Not yet. We're going to check it. We're going to do it first, but we're going to check and show that we are doing it correctly. All right, here's how degrees, minutes, and second works. We have our degree symbol, the open circle. Minutes is a single comma, or apostrophe, I should say. And then seconds is like the double apostrophe. When measuring an angle in degrees, fractions of a degree are often represented in minutes and seconds, no relation to amount of time. Degrees, minutes, and seconds are often used in navigations for things like latitude and longitude on topographic maps. So guys, when you think about it, if you think about 360 degrees, think about a coordinate plane, right? Think about this being a radar system, and you got like a ship somewhere over there, right? Well, if that ship goes down and needs help, when you think about the grand scheme of the ocean, it's gigantic. So when you want to figure out, oh yeah, it's somewhere between 0 and 90 degrees, it doesn't really help people trying to find this ship because that's a lot of ocean to try and narrow down on. So what they do is, if you can picture this, they take 1 degree, that's probably even too big, out of 360, right? So let me just blow up 1 degree. This is 1 degrees. They take 1 degree and they chop it into 60 individual sections. Each one of those sections is a minute. So now just picture 60 like subsections, right? Now they take each one of those minutes, each one of those 60 subsections, and they cut each one of those subsections into 60 more subsections. Each one of those is a second. So by narrowing it down, they're going to get this Mayday ship into this very defined area of like, oh, it's at 12 degrees, 15 minutes, and 82 seconds. That's what they're going to be able to narrow it down, so it's that much easier to find where that ship is. So we have to kind of convert, well, how did they break it down? How many seconds, how many minutes are inside of each degree? So we can use it to convert back and forth. All right, so in a full circle, there are 360 degrees. Each degree is split up into 60 equal parts. Each one of those parts is 1 minute. So 1 minute equals 1 minute. They use the single apostrophe is how we denote 1 minute. So 1 minute, it equals 1/60th of a degree, right? We take 1 degree and we chop it into 60 equal parts. Each one of those parts is 1 minute. So therefore, 60 minutes live inside of 1 degree.
What is he like right next to the one that's like 1?
It's 1 with like an apostrophe. That's how we denote 1 minute. We use a single apostrophe to denote a minute. All right? And then we take it and we break it up even more. Then we take each one of those 60 minutes that live 60 minutes live inside of 1 degree. We take each minute and we split each one of those 60 minutes up into 60 equal parts. Each one of those are called seconds. So 1 second, which is equal to the double apostrophe, it's equal to 1/60th of a minute, not of a degree. It's 1/60th of a minute. There are 60 seconds in each minute, and then there are 60 minutes in 1 degree. So 60 times 60 is 3,600. So that means there are 3,600 seconds living inside of 1 degree. Oh, I already have the symbol there. So those are your 2 big conversion factors. You're going to have 1 minute equals, I'm sorry, I shouldn't say that, 60 minutes. That's my bad. 60 minutes equals 1 degree. 60 minutes live inside of 1 degree. And then you're going to have 3,600 seconds equal 1 degree. And again, this is 60 minutes. And this is 3,600 seconds, in case you forget the notation. All right, ready? All right, so they want us to take degrees, minutes, and seconds and just convert them to straight up degrees. What does this equal in just a degree measurement? All right, so here we go. We're going to break this up into 45 degrees. It's already in degrees. He's the good guy. We keep him. Then we're going to say plus, we have 10 minutes. We're going to have to convert 10 minutes to like a fractional part of a degree. plus we have 15 seconds that need to go back to degrees. So guys, it's just a conversion factor. Do you guys remember this is my favorite part of chemistry, like the canceling out of like centimeters, and you end up in meters. It was my favorite part. So take this, it's 10 minutes, right? So it's times your conversion factor. I'm trying to end up in degrees. So 1 degree was equal to 60 minutes. So now when you do it like this, your minutes cancel and you're gonna be left with degrees. So it's 10 over 60. You have 10 out of 60 minutes there that make up 1 degree. So if you take 10 and divide it by 60, it converts it to degrees. Plus 15 seconds, right guys? 15 seconds, what's that conversion factor? Well, we're trying to end up in degrees, right? 1 degree was equal to 3,600 seconds. So now your seconds cancel and you're gonna be left in degrees. So you have 15 out of 3,600 seconds that make up a degree. So then it's 15 divided by 3,600, and then you'll be in degrees. So guys, all you have to do is ask your calculator to do this. Do 45 plus 10 divided by 60 plus 15 divided by 3,600, and it's gonna get you a decimal. So I might be able to bring this up on my screen. Just ask your calculator what that is. So you're always taking your minutes, dividing it by 60, and you're taking your seconds and dividing it by 3,600. So again, we have 45 plus 10 divided by 60 plus 15 divided by 3,600. Hit enter, and it's about 45, they keep 4 decimal places on the homework. It's 45.1708 degrees. So that would be 45.1708 degrees. And you've taken your degrees, minutes, and seconds and converting it all back to degrees. Let me just get that off the screen now. All right. I'm gonna skip this one and let you guys try it. I'll have it on the filled in one. But again, you would just do 50 plus 6 out of 10 plus 21 out of 3,600. That's all you have to do. Minutes always get divided by 60. Seconds always get divided by 3,600 because that's the conversion. All right, I'm gonna come back to your calculator in a second. Let me just do this last one just so I can talk you through it. All right, now they're giving you that's one that's already in degrees. And they want you to convert it to degrees, minutes, and seconds. All right, well, guys, think of it like this. 12 degrees is already the whole number part, right? So we already have 12 whole degrees from 12.87. Then we're going to take plus the 0.87 degrees, right? We just break it up between the whole and the decimal. The decimal is what we're going to convert to the degrees, minutes, and seconds. This will stay our degrees. The decimal part becomes our minutes and seconds. All right, well, guys, let's use our conversion factor, right? So first we got to get to minutes, then we can get seconds. So we're going to take 0.87 degrees, and we're trying to convert it to minutes. So think about it. That's 1 degree, which is equal to 60 minutes. So our degrees will cancel, and I'll be left with minutes. So you have to ask your calculator, what's 0.87 times 60? I think I remember it, but I don't want to. Is it 12.2? 52. 52.2? Okay. Go ahead, if somebody raised their hand.
Can you repeat that last step?
Right here?
Yes.
The decimal of the degree, we're going to convert it to minutes first. So we have 0.87 degrees times the conversion factor is 1 degree is equivalent to 60 minutes. So the degrees will cancel and we'll end up in minutes. So all you really have to do is 0.87 times 60. And you're going to be left with 12 degrees plus, what did we say, 52.2? Was it 52.2? Okay. And we're in minutes now. So that's where we stand. This got us to minutes. So 12 degrees plus 52.2 minutes. So guys, now the decimal of the minutes is what we're gonna convert to seconds. So now we're gonna have 12 degrees plus 52 minutes plus 0.2 minutes left over. And it's the 0.2 minutes that we're gonna convert to seconds. So now we're gonna take 0.2 minutes, but we gotta convert it to seconds, times, well guys, 1 minute is equal to how many seconds? 60. So the 3600 doesn't get used here, it's always just timesing by 60. So now you have to do now my minutes will cancel, and I'll be left in seconds. So what's 0.2 times 60? And you'll end up with 12 degrees, 52 minutes, and what was 0.2 times 60? 12, right? 12 seconds. Now, let's pretend 0.2 times 60 was a decimal. Just round the seconds to a whole number if it was a decimal. All right, and you get 12 degrees, 52 minutes, and 12 seconds. So here, you're dividing by 60, you're dividing by 3600. Down here, you just keep timesing by 60 because there's 60 minutes and then 60 seconds, and you just keep converting the decimal to the next configuration. First decimal goes to minutes, the next decimal goes to seconds. All right, and now on your calculator, let me show you this, just so you can check it. On your calculator, I'm going to do the first one. Guys, if you put in 12.87, just type it on your screen. $12.87. If you hit there's an angle button up here. You have to hit second and apps to get to angle. Second and apps. See this DMS? It's going to take 12.87 and convert it to degrees, minutes, and seconds. So either scroll down or hit 4. And I wanted to take 12.87 degrees and convert it to degrees, minutes, and seconds. And it's 12 degrees, 52 minutes, and 12 seconds. Now to go back, if you go back to the first example, what was the first example? What was the first one? 45 degrees? Was it 45?
Yeah.
All right, so if you put 45, guys, go back to that second apps button. See, this one is degrees. Hit that, enter. So it's 45 degrees. What was the minutes? 10 minutes. Go back to that second apps. See, the second one is number 2 is that apostrophe. There's your minutes. And then what was the, oh, I didn't hit it.
Ma'am, please call the main office.
Always come in a rush. Degrees, what was it? 10?
What button are you pressing?
Second apps. Number 2. There's minutes. And then what was the seconds? 15. Now, don't ask me why, but the seconds is in green above the plus sign. So you have to hit alpha and then the plus sign to get your seconds. And then hit enter, and there it is all in degrees. I am so sorry. I always go over, guys. I'll show you, Michael. Just give me a second. So again, on your homework, I only made you guys do degrees, minutes, and seconds, and angles of rotation. I'm pretty sure I saved radians, but either way, homework isn't due until Wednesday because I knew I wouldn't finish today's notes. If anybody struggles with this, please just text me and reach out. I know that was quick. All right? But you are good to go. I hope you have a great day back. You too, guys.